everyone. Welcome to Foresight Space Group. Today, we're really lucky to have Mariam Naseem here, and she'll be talking about how habitability on Earth can inform habitability on other planets. With that being said, please take it away, Mariam.
Yeah, thanks so much, Lydia. I appreciate the opportunity to speak with your group here today, and thanks for organizing this. A little bit of context about myself. I'm doing a PhD over at the University of Maryland College Park, doing some research in collaboration with NASA and Goddard, and I'll be talking about that here shortly. But if you have questions or are interested in what I was doing before the PhD, we can talk about that as well. Let me just share my screen again. Okay, there we go. So the topic today, I'll be talking about some fieldwork and lab analog studies that we've been doing, our group, and how this might inform thinking about habitability on icy ocean worlds. The overarching theme of my work is astrobiology, which is the study of the origin, evolution, and distribution of life in the universe. And this is a very broad category, but within that, there is the search for habitable locations where life may exist beyond Earth, because today we only have one sample size of where life exists in our entire universe, as far as we know, Earth. And thinking about locations as close as even our own solar system where conditions may exist to host life is one of the topics that researchers are interested in. And we think based on a few sort of elements. Is there water? Are there bioessential elements? Is there chemical energy? These are some of the components based on our understanding of what life needs on Earth that we look for when we think about habitable locations. One such class of locations is ocean worlds. We are considering them as potentially habitable targets. An ocean world is a body with a current liquid ocean, not necessarily global. And we believe these ocean worlds exist in our solar system based on spacecraft data. Here's a cross-section of the Enceladus moon, which is one of the moons of Saturn. It's an artist's rendition. And based on Cassini data, we think that there's a global ocean beneath kilometers of water ice, which is very interesting because on Earth, like oceans are basically one of the locations where a lot of life exists. And even though there's all this ice that's covering the ocean, there is potential that hydrothermal vent systems and other geothermal inputs may be producing chemical energy that could fuel life in this environment still. And this has led NASA to consider these as interesting targets, the community. So researchers have recommended to NASA that these bodies need to be studied. And in turn, this leads to different efforts on Earth in the lab, modeling studies, fieldwork, like I'll talk about, to begin to understand some of the science objectives and measurements that future spacecraft mission to these ocean worlds may want to explore. So with that context, the first project I'm going to talk about is some Arctic radar fieldwork we did that may have implications for Europa. And what is Europa? So Europa is one of the moons of Jupiter in this case. Is much smaller than Earth, so very small, like diameter compared to Earth. And yet it has up to, we believe, based on spacecraft data from the Galileo mission, that it may have as much as twice the amount of liquid water that exists on Earth. So some of that density data that they saw and magnetic field measurements are indicating that there might be this subsurface global liquid water ocean on Europa. So that was a lot of context, but here I'm going to talk about some radar field work we did that has implications for Europa. So Europa is one of the moons of Jupiter. It is believed to have almost twice as much water as Earth, and on Earth, our oceans are teeming with life. So if there's liquid water and that much liquid water in Europa, it's an interesting target body to be studying. In fact, NASA has launched the Europa Clipper mission in October of 2024, so very recently, and it's making its way to study Europa. It's going to be an orbiter mission, and it will be looking for potential signs of habitability. And this brings us to the field work. So on these icy ocean worlds, yeah, we have the global liquid water ocean, but we also have a lot of kilometers of ice that encircles that ocean. This is an artist's rendition of a cross-section view of that icy structure, and then beneath it, this liquid water ocean that we think exists. And there's a lot of near-surface targets as well within the ice that are potentially interesting for habitability. I've pointed out some of these locations here, like shallow brine liquid water pockets, because the salts in these liquid water pockets may be depressing the freezing point enough that this is a stable liquid body within the ice that could potentially be hosting life. The ice-ocean interface is also another interesting target because at that interface, we have that phase transition happening, but also potentially concentration of nutrients are happening at that interface, and energy might be getting produced because of redox reactions from different reductants and oxidants mixing at that interface that could potentially fuel life. So these are some targets that are interesting for Europa Clipper as well, which is going to have a radar instrument on the spacecraft that's going to be looking at near surface and potentially that ice-ocean interface depth with the radar. And what we did is we went to an analog site on Earth. So we went to the Beaufort Sea on sea ice. This is in the Arctic Ocean, and it has it's ice covered most of the year. We took a radar instrument ourselves. This was ground penetrating radar. So unlike the orbital radar that will be on Clipper, for example, we took ground penetrating radar, but our goal was to study how the sea ice internal structure may vary, what that signal looks like in salt contaminated ice using ground penetrating radar, as well as its thickness if we could track that ice ocean interface on the Arctic sea ice. And broadly, it's an interesting thing to do because we wanted to see the signature of that saline sea ice using a radar instrument. Because when you have salt in the ice, it tends to dampen the signal strength. We call it attenuation. And we wanted to see if these characteristics like structure and thickness would still be visible despite that. What we did is we took commercial ground penetrating radar out there, multiple frequencies, and these are basically electromagnetic waves, the radar waves. This is our setup. That's actually me with my collaborator at NASA Goddard. And we had hooked up, it's interesting, this is actually a baby stroller that we've repurposed. We have the antenna and we're dragging it on the ground. And based on the dielectric properties of the subsurface structure, you can see reflections of your electromagnetic waves. And you get a signal called a radargram, which is what we've plotted here. But that basically at a high level, it's a map of subsurface structure. Where we went, so we went out, as I said, to the Beaufort Sea, and this was last year, so last March 2024. Just the layout of the camp. It was interesting because we had access to both first-year ice and multi-year ice on this location. I'll talk to you about some of that in the next slide. Most of our field operations were near the 10th year, where I've marked, and we did a number of radar scans, so different survey geometries, multiple frequencies, all in this goal of trying to map the sea ice internal structure and its thickness. Let's talk about the multi-year sea ice. So as I mentioned, there was two types of ice that were present on this ice flow. This ice has survived one or more summer melt seasons, so there's a lot more variation in the terrain. There's ice peaks, there's pressure ridges, a lot more snow cover. Thickness was varying quite a bit. Whereas first-year sea ice, it was fairly uniform in thickness, we noticed. And this is ice that is more newly formed. It hasn't really survived a summer melt season. So visibly, you were able to see differences between the ice, but then let's see what we saw in the radar. This is one of the long traverses, this purple line, where we actually went over both multi-year and first-year ice. And we were actually able to track quite easily. You can see that variation. The orange dots are what marks the ice-ocean interface based on our radar ground here. And you can see that transition point from multi-year ice thickness, where there's a lot of variation, a lot of internal structure, onwards to the first-year ice thickness, which did not vary as much and was less thick. But that was very interesting because we wanted to test and see if we were able to detect these different structures as well as the performance of radar on this salty ice. Another thing is the anisotropy of the sea ice, so how the ice forms and how that may be affecting our radar return. The sea ice, so columnar sea ice, which typically exists in the Arctic, it encloses brine, which is concentrated salty water, perpendicular to the crystal axis. And you can see these inclusions, like dominant inclusion directions for the brine, and that tends to dampen the radar wave. So it will affect the signal strength of the radar wave. affecting the detection of that ice-ocean interface I talked about. It also tells us something about how ocean currents may be driving the alignment of these brine pockets and crystals. We have some previous work that has been done. It exists in the literature where scans that are done in one direction, so in that direction parallel to the brine inclusion alignment, tends to extinguish that ice-ocean interface that we're interested in. Whereas scans that are done perpendicular to that inclusion alignment, you begin to see the interface again. So there's a bit of this directionality, how you do the radar scan relative to the sea ice structure and where it's trapping salty water will affect the returns for that ice thickness parameter, ice-ocean interface detection that we're interested in. We also did some azimuthal scans, so we were trying to change direction of our scans and see how that might shed light on the internal ice structure here. One of them was this A prime circle we mapped out. And here at the 1 meter depth mark or so is where we see that ice-ocean interface in this case. But you can see patterns of the thickness where it's higher signal strength, and then the signal strength begins to decrease. So there appears to be some of that anisotropic effect here as well in the sea ice that we went to for our radar scans. And now we'll talk about the implications of all of this. So you heard a lot about the Arctic and fieldwork out there. How might this relate to Europa again? We talked about Europa having quite a big ice shell, kilometers thick by some estimates. We believe that ice shell is also salt contaminated, something I initially talked about. And so by doing these radar scans on Earth, we begin to see this relationship between how you do your radar scan. So there's this dependence between the azimuth of the radar scan and how well you're able to detect your ice-ocean interface. And if you recall, mapping that thickness of ice is something that's important for Europa Clipper as well. Trying to understand that influence of directionality and the internal sea ice structure on detection by radar will help missions like Europa Clipper that also have radar instruments understand if they need to basically be doing their radar orbit traverses in certain orientations, potentially interpreting that data, and also for future landed missions. So currently there isn't a selected mission that's planning to land on Europa, but there may be in the future. And if that mission that's planning on landing to Europa thinks about including a ground penetrating radar instrument, it would be especially relevant. This kind of work would be more analogous to what they might be thinking of doing in that case. So that's some context for this work where we went out in the field. Now I'm going to switch. So this is a completely different project. And it's related to the other icy moon I talked about, which is Enceladus, a moon of Saturn. Enceladus, for context, now we're way out further in the solar system, much smaller than Europa as well. Also, what we believe to be an icy ocean world based on Cassini data. So the Cassini mission went out there, it was studying Saturn and its moons. And around 2006, when it was orbiting one of Saturn's moons, Enceladus, it detected a liquid water vapor dominant plume erupting from Enceladus's south pole. And this plume, it went through the plume, it sampled some of the composition of its grains, and it realized that based on the spectral data we're seeing, these grains are salty. They may be potentially containing these salts I've mentioned on our slide here. And there seems to be now this evidence in case of Enceladus between that liquid ocean I talked about that may exist to the surface of space through the eruption of this plume. And that led us to our second project here, where we were curious if the erupted surface materials on Enceladus, so what we are sampling out here in space in the form of this plume, say, how different in chemical composition is that from the original subsurface ocean? And this question is important because understanding those changes in composition that may be occurring will then allow us to infer what relative abundances of compounds are within the ocean, and hence the ocean composition, its pH, its salinity, all properties that help to determine whether an ocean is, for example, a habitable location for life. I talked about cryovolcanism on the first slide. This is basically cryogenic volcanism. So on Earth, we have eruption of molten lava. On these icy satellites, because of the temperatures at their surfaces, you have frozen like eruptions of the liquid water and vapor that's erupting is basically freezing. And that's what's driving this plume activity. During this eruption, the question we were particularly focused on is whether there was a change in abundance of compounds, as I said, in the erupted material versus that parent ocean during vacuum exposure. Imagine through these ice shells, like how is the eruption getting to space? Like where is that liquid traveling through? We think that there may exist within the ice shell what we call pathways or conduits. This is a schematic representation of one such conduit where you have this water coming up from the ocean. Then at the triple point, we think that pressures around at the triple point here in the conduits may be resulting in the formation of this vapor for the plume, and that plume is now erupting into space. And particularly looking at when that liquid to vapor transition happens, how relative salt abundances, for example, are changing between the ocean and grains or organic compounds. And why these two classes of compounds? Because organic compounds and salts are of interest in biosignatures. So when we think about planning future mission concepts like Enceladus, one of its science objectives is, for example, thinking about the relative abundances of organic compounds that they sample in the plume or salts, and how that may tell us something about whether the signal is from biology, so a biotic signal versus abiotic, not from life. And the salts, as I mentioned, will help us understand salinity, pH, and potential ocean habitability. So how do we simulate this in the lab? We call this the SOCR, the Simulator of Ocean World Cryovolcanism. As I said, the goal for this was to look at salts mostly, and we had a synthetic two salt system, so a binary salt system that is similar, using some of the salts that we believe exist in Enceladus's oceans from the plume grain data. And we have this set up in the lab where we create a vacuum, so the solution gets injected. This is a picture from the lab setup. It goes into this vacuum chamber where we bring down pressures below the triple point of water. So try to simulate the vacuum environment that may exist in those conduits or pathways in the ice shell of, say, Enceladus, and then see what happens to this injected liquid. It vaporizes. What we're left with is residue that contains the salts. Then we analyze that salt. So here's some collection cups that the salts are collected in, and we analyze some geochemical parameters of those salts, the pH, the salt concentration, and we're able to infer by matching that with geochemical modeling data what the composition of one salt versus another is in the plumes. And as I said, these are binary salt systems that I'm injecting for now. In this case, I was looking at chloride versus sodium carbonate compositions in the salt. And I think I spoke about this already, where the injected solutions were to match Enceladus's ocean compositions that we think exist, and the concentrations we chose were also based on plume grain data. Across a few of the initial experiments we did, so we've done a few preliminary experiments injecting it into that setup I showed you for this two-salt sodium carbonate, sodium chloride system. This is another schematic view of our injection line pathway, so all the way from the starting solution to the different points along the line where we can sample and collect residue. And initial trends are showing us that down here in the chamber where the vacuum is lowest, there may be relative enrichment of chloride. So the concentration of chloride in that residue may be higher than the carbonate mass fraction. And it's interesting because bringing it back to Enceladus, for example, where subsurface liquid water is saturated in salt, there may be higher proportions of sodium chloride versus carbonate in the erupted material than what might exist in its subsurface ocean. So this may be one implication for the trend we're seeing, to be determined with follow-on experiments, but it already begins to tell us a little bit about how these salt systems that exist on Enceladus may be getting altered by the vacuum ejection and this plume eruption process, and what that might mean for compositions of these compounds in its ocean. And that's particularly interesting for two reasons, because Cassini, as I mentioned, already sampled salt-rich ice grains in the plume of Enceladus back in 2006 or so. It may help with interpreting that data for the salt compositions that we already have from that mission and applying these alteration factors or fractionation factors, we call them, to then back out the ocean compositions for better estimates for that. And I talked about Enceladus Orbilander. Enceladus Orbilander is a mission concept. It was one of the top mission concepts that was recommended in the recent Planetary Science and Astrobiology Decadal Survey. This is a mission that would then plan to orbit Enceladus as well as land on its surface. And one of its key science objectives is also thinking about the abundances of these inorganic species, like the chloride carbonate species that we're testing in the lab. And they explicitly do mention that looking at these measurements will then help determine, as I said, like pH, temperature, and salinity of Enceladus's ocean. So it may help interpretation of past data as well as these future mission concepts. And with that, it was a pretty short presentation. I hope it made sense and you enjoyed it. I'll leave you with this question. As you're thinking about space, what are some of the analog settings or processes that you could simulate on Earth for your research? A lot of this is modeling focused today. There's a lot of like people doing models because you can use those environments to extrapolate to conditions in space more easily. But how could you incorporate some of these elements in the lab or in the field to supplement your modeling efforts, for example? So that's all from me.
Great, thank you. I think we have one question in the chat right off the bat
Sure.
from Kyle. Kyle, do you want to come on and ask your question?
Sure. Hi, Mariam.
Hi.
With respect to your GPR observations, I'm not much of a
Oh,
GPR
good,
guy.
Khalil. Nice to see you.
Likewise, does GPR control for polarization in transmission and receipt?
Yeah, that's a great question. Here, these ground penetrating GSI systems we're using, the polarization, I would have to double check the exact like specs for it, but I know in previous studies, they actually, when they built the GPR system themselves, they actually had to think about dual polarization in order to detect that interface. So orientation of transmission in both directions, because as you saw when I was presenting, if you scan in one direction versus another, you don't see the interface anymore. With our GPR, we literally had to do physical scans in both directions, but some systems that have been designed from the ground up may try to include that dual polarization in the outset in the design. But I don't know off the top of my head right now the polarization for the system we used. I would have to double check.
Okay, that's fine. I was just curious because I thought it was very interesting, your extraction of the salinity and the discussion of the voids.
Yeah.
That's exactly where my mind starts to go with that. I know from like an imaging radar perspective, polarimetry starts to become very powerful for age of sea ice.
Okay.
But you're doing things with the radar that I have very little concept of. Completely curious.
Yeah, no, I can also, Kyle, I can send you the specs because this is like commercially available off the shelf radar. So I could send you the instruction manual for the specs on this. They don't always tell us about the inner workings, but there's some information in there for sure that will help with this. Yeah.
Nice. Very cool. Thank you.
Thanks, Kyle.
Great
Nice to
work.
see you. Thanks for joining.
Very nicely done.
Awesome. Micah, I think you're up next.
I have a very novice question. Do we expect the thickness of the ice on these moons to be similar to the thickness ice on parts of the Earth, or is like an order of magnitude difference?
That's such a great question. Actually, it's not a novice question at all. It brings me to this point about that analog and the fidelity of analogs. Like the thicknesses on Earth, for example, the thickness we were looking at in the Arctic in the order of meters is nowhere comparable to what we think the thickness of ice shells on these ocean worlds is, which is in the kilometer range. So it wouldn't be an analog for, say, how deep that radar needs to penetrate in order to get to that ice ocean interface. But it does tell us something already about near surface ice structure and internal structure. So some of the radar, there's two frequencies on Europa Clipper. One frequency is going to do more near surface depth penetration, and the other one is going to go deeper. Specifically, the one that is going to be looking at shallow structure, our work might help inform some of their interpretation. But yeah, that's the thing with an analog. It's hard to find locations on Earth where ice structure and depth is going to be as deep as what we might expect on these icy ocean worlds. There are a few places that are higher fidelity. People go to a number of locations. There's Lake Vostok, which apparently is around 4 kilometers of ice. And then there's like this subsurface subglacial lake that exists. but it's hard to get out to these locations. Accessibility is always a factor as well when we think about analog studies. But thanks for that question, Micah.
It's still much more accessible than Europa. So
Yes, exactly.
Are there any other questions?
I do have another one if no one else
Okay,
has
great.
one.
Hit it, Micah.
Is there seasonal surface ice melting on these moons, or is it just there's no melting whatsoever throughout its life?
Yeah, that's another great question. It's really so cold there that it's not like Earth where, for example, the Arctic, where there's like seasonal cover and then ice melts and you begin to see an ocean underneath. As I said, there's like literally kilometers of ice there. The temperatures are so low that overall that ice structure is maintained over geologic time. But within the ice itself, there may be impurities. So remember I talked about salts. Salts within that internal ice structure may be lowering the freezing point in certain void spaces or areas where water is intruding into the ice shelf from below, from that ocean. So we may have these shallow liquid body like habitats or pockets within the ice, but overall that structure is not melting at the scale of, say, how sea ice melts in the Arctic on Earth, if that makes sense.
Yep, thank you.
Thanks.
Oh, Creon just joined. Hi, Creon.
So I have one quick question. This is Ron Turner.
Sure.
So very good presentation. I appreciated it. One of the nice things about doing these analog studies is it's really good to get some ground truth that uncovers the real messiness of the real world, right?
Yes.
It's so just so in case you don't know, I'm senior science advisor to NIAC, and so we get lots of proposals. And of course, since our ideas are often just far out there, they have to use pretty simple models for doing their assessments. And as always, the devil is in the details, and you've got a good example and some good illustrations of just how complex this could be. Given the complexities that you've uncovered, how confident are you that Europa Clipper is still going to give us some clear information?
Yeah.
Either of the two bands.
Yeah, that's such a great question. I was actually talking about that at a high level. I asked a similar question actually to the PI of the Reason instrument. So the radar instrument on Europa Clipper is called Reason. And as Ron mentioned, it has dual frequencies. So there's a 9 megahertz antenna as well as a 60 megahertz antenna. And I asked Don Blankenship is the PI of the Reason instrument. I was asking him, say that this ice shell structure, it's heterogeneous, it may contain these salty impurities. We all know that's going to attenuate radar signal. That's well known. And he was saying that they do a lot of, like you said, Bron, they do a lot of modeling studies as much as they can based on the parameter space that we think exists today for what kind of ocean composition may exist, what kind of salts may be intruding into the ice shell, attenuation coefficients that we already know. They try to model for the frequencies of the antennas on Europa Clipper, how that radar signal will perform when it's penetrating the sea ice, Europa's sea ice in this case, in these environments, in the presence of these impurities. So to the best of their ability, there's a lot of studies they do to characterize that performance ahead of time. But like you said, the reality is that we don't always know what we don't know. And there will be new things that they see when they get to Europa. And in this case, that's why we do what we're doing today, because it can help them anticipate, like you said, some of that messiness that may occur in the data and how to begin interpreting that.
Very good. And if something occurs to me in the meantime, are you going to be at LPSC in next month?
Yeah, I am, Ron. Will you be there?
That's my plan.
Awesome. Yeah, please stop by. I'll be presenting the cryovolcanism lab work, so I'll have a poster at LPSC.
Okay, great. I always make a point of hitting the posters as many times as I can, so I'll look forward to it.
Wonderful. I'll see you there.
Are there any other questions from the audience?
I certainly have one. I'm sorry I tuned in late. I had another meeting, but do you have any comments or thoughts, reflections on New Horizons? Because that's certainly a cryo world.
I know that New Horizons was mostly focused on Pluto, and I know that it's in its extended mission. That's about what I know at the moment. With Pluto, I don't actually study Pluto, but I know that there's a lot of interest in the different types of ices that may exist on its surface. But that's a bit the kind of the extent of my knowledge with New Horizons and Pluto at the moment.
Yeah, methane ice, CO2 ice,
Yeah,
some liquid somewhere, probably.
probably. Yeah. I actually don't know if New Horizons has a radar instrument on it. I would have to look into that. I don't think so. Yeah.
Have you been involved in any studies of the radar, of Mars radar stuff? Because there they have at least questions of subsurface ice and subsurface water even.
Yeah, that's a great question. So on Mars, some of the radar instruments I've heard of is Charad and Marsus, my collaborators. So in that picture I showed you where there was me and one other individual on the Arctic sea ice, she's actually worked on Mars radar. So she's looked at that data and how that may inform the signatures for ice on Mars's surface. But I don't do that myself. But from her, I know. And the other interesting point is that based on that structure, if the radar instruments on these Mars missions is what they use then to build on that heritage for the Europa Clipper reason instrument. So there's always that sort of building on knowledge of previous missions that goes into radar instrument design.
What's her name, by the way? Because we had a Mars radar person at Planet for a while.
Her name is Emily Shoemaker. She's over at Goddard and she's a postdoc there right now.
Okay, different person.
Yeah.
I think Li Shan has a question. Do you want to ask that?
It's got a picture of ice.
Yeah.
Oh,
Oh, the mic doesn't work. I'll just read the message out loud and you can respond to the group, Mariam. Question of local intervention from scientific study. Maybe cryo worlds do have microorganism lives. How do we confirm that there is no intervention from Earth-based life forms? We could literally kill the only example of life outside Earth.
Yeah, that's another really great question. It's something that goes a lot into how we think about missions. Personally, I'm not involved in that area, but planetary protection is the general umbrella under which this line of work falls. So making sure that before you launch your spacecraft into space, it is thoroughly decontaminated as much as possible. So all the operations are typically in a clean room environment. There's different cycles that the spacecraft has to go through before it's launched to minimize that Earth micro contamination aspect of things, which is what the question was alluding to. On the other hand, and there's also different planetary protection classes for these bodies. So places like Europa, where it's a high target for potential life and habitability, the planetary protection requirements are stronger. And there may be more steps you need to go through before you launch a spacecraft, say, to that body, or before you get approved to do certain operations when you're reaching that body, compared to, say, the moon, where the planetary protection requirements may be a little bit lower because, as far as we know, the environment is not conducive to life. The reverse is also interesting because, say you do find something out there on Europa or some of these asteroids we've been visiting, there's also planetary protection rules and requirements for bringing samples back to Earth and preventing contamination in that direction as well. And there's a lot of literature and documentation that exists under this umbrella of planetary protection, and it's managed by, I believe, COSPAR, the Committee on Space Research.
That's so interesting. This is a broad question, but you mentioned contamination and the rules and regulations required to bring samples back. Have we had any run-ins like that before?
the only place we brought samples back from is the moon
Oh, okay.
and the tail of the comet, things like that.
Right now, we've also recently brought samples back from Bennu. So the Osiris mission, brought back samples from Bennu. And then there's another one from Ryugu. So that's another asteroid sample return mission that brought back samples from there. As far as I know, again, I'm not an expert in that area, but it's not like we've discovered life, because that would be news. Like, we have not discovered any signs of life on these samples, but there are certain organic compounds of interest that they analyze, and the requirements to keep those samples in a pristine condition, even on labs on Earth, in order to analyze these components without, say, atmospheric contamination from Earth, is something that people think about.
Yeah, because you could end up with a terrible situation where you detect life in the sample on Earth, but it was life that just contaminated the sample after it got to Earth.
Yeah, so definitely all of that goes into planning and thinking about how to analyze these samples. But so far, we are still searching for life beyond Earth.
Nozer, I think you have a question. Go for it.
Hi, Mariam. Very nice talk. Greetings from Berlin.
Okay.
My question is, you use sodium chloride probably and carbonate salts in your experiment. How about the phosphates? Because we just discovered last year the sodium phosphates. Do you plan to extend your experiments to other salts category? This is my first question. And the second relevant question is about organics,
Yeah.
about the mixture of salts and organics in your experiments. So would you comment on that?
Yeah, and it's really great to see you. I've read your papers. I know the paper you're referring to, the postbird paper in Nature. So thanks for your question, firstly. Secondly, yeah, I mean, based on that paper, as you said, phosphates were present. Currently, the plan is not to test phosphates in the system, but I was actually thinking of extending the work even beyond Enceladus because there may be potential plume activity that we don't know yet. It needs to be confirmed, maybe potentially existing on Europa based on Hubble Space Telescope data. So I'm thinking of some salt systems relevant to Europa based on surface compositions, as well as Ceres, because we see all these carbonate, ammonium chloride, ammonium carbonate deposits on Ceres. So I have a number of salt systems in the works, but to extend my work to other bodies. And your second question was about organics. Yeah, we are considering organics. There's a paper published by our group using the setup I showed, Nouveau et al. 2024, where we did experiments like what I'm discussing, but with amino acids and fatty acids. And those results are published. It was synthetic systems. Some future work that I'm thinking of doing may be looking at natural samples as well.
Yeah, that would be great. Thanks for that. I look forward your results. Just to one comment, because I'm also starting to build some experiments because just got a big European funding there to build the whole simulator, the whole in the lab. And I look forward your work, and I will contact you for that as well.
Yeah, I'll keep an eye out. That's amazing. I would love to be in touch and learn more about what you're doing for potential collaboration and our work in this area. Thanks again for your question and your interest.
Thanks. Bye.
Great. I think, Carol, it's great to see you. Do you want to ask your question?
Yeah. Hi, Naseem. Mariam. Everybody in NASA usually see the last name first. So I'm interested in this field camp on the Beaufort Sea.
Sure.
Was there an actual field camp? It looked like there was an ice runway. Did you stay in tents? Did you stay in, especially if it's seasonal, that the ice is not melted?
Yeah.
And I'm assuming you must have gone there in the middle of winter, right?
Yeah, these are all great questions, Carol. So let me start from the beginning. This camp, it was a camp. It was a program that was advertised by the U.S. Navy Arctic Submarine Lab, so U.S. Navy ASL, they go by that abbreviation. And they set up this camp every 2 years on the Beaufort Sea ice. It's by the Navy in order to do submarine training exercises. So they have really huge 100-person or so submarines that breach the sea ice and do military exercises out there. And they have to set up a camp to do those exercises. And then they put out a call because they're already setting up the camp. They have the infrastructure for researchers to join them while they're out there in the campaign. We put in our proposal in that call that they released, and we were selected to go there. We just had to go all the way up to the Prudhoe Bay in Alaska commercially. And then from there, it was with the US Navy. So they flew us out onto the sea ice in their Twin Otter planes. They had the camp set up, so they were in charge of the logistics on site. Our safety, as you mentioned, is the sea ice. It is in March, so it was pretty thick at the time. It was pretty cold, but even they're the ones who are making sure that it's all tracked, that there's no fractures and like cracks in the ice where they set up the camp. They also provided the polar bear guard because there's literally polar bears out there. So a lot of the safety, logistics, infrastructure, and survival support on the ice was with the Navy.
Thank you.
They were friendly.
Yeah.
They were friendly.
Who, the polar bear? There were no polar bears. The Navy was friendly, yes. They were really fantastic. It was really wonderful to work with them, and they were just really great enablers of our science.
How many science teams were out there? Were you the only one, or were there others?
It's limited. So most of it is the Navy people and the other military. So they invite people from the Army and other campaigns that want to do extreme weather training out there when they set up the camp. The science team was pretty limited. I think there was around 10 of us or so at any one time. The camp was for over a month. And in that period, they would rotate out science teams. So they maybe 10 for 2 weeks and then maybe another 10 for the next 2 weeks.
And were you provided with survival gear and that kind of stuff, or did you have to figure out what to bring?
That's another great question. In terms of basic sort of survival kit, they gave us one. So that had the sleeping bag, the tent in case there's an emergency, a fire starter, some basics that you need. And they do provide some training before we went on the ice. But in terms of the extreme cold weather gear, so the parkas, the boots, the mittens, like the everything else for yourself that you need, we had to provide. And because my advisor does a lot of polar field work, he's been to Antarctica, he's been to Greenland, we didn't really have to purchase anything new. We just used what existed in our lab.
Thanks.
Yeah, thank you.
You want to go, Carol?
Maybe next year.
You could sign me up anytime. That'd be great.
Yeah, it was great. I would recommend it. It's every 2 years though, so it's not very frequent. And they don't always put out the call every year. For example, this time they're doing torpedo training exercises, so science involvement is limited.
Did you see the submarines breach?
I did. I wasn't there in person, but the teams that went out to help them, they showed us some pictures and we see it from the plane. So when we were flying on the Twin Otter to the field site, you can actually see the top of the submarine breaching the ice. And I have pictures, which were pretty cool. It's just amazing the scale of it. It's so big.
Can we ask? I have one more question if we have time.
Sure.
What's next? Like, you got this conference poster and you've got your current situation in this lab. Do you have your sights set on some next steps for your career and your research?
It is a good question. It's interesting for me because I come to this PhD much later in life, actually. So I already have an MBA. I've done engineering work. Even within aerospace, I've worked on the commercial side and with government. So I used to work briefly at the Canadian Space Agency before moving here to DC to do this PhD. Right now, I'm still early on. So I've only done a few years at the PhD. So there's still a ways to go. So next steps is finishing the PhD. But after that, I think opportunities where I can bridge those gaps, like between industry and academia, some of my insight from the business and policy side, I'd probably try to look for interdisciplinary roles and science leadership where I can bring maybe all of those aspects and experiences I have in my career to fore. So I'm not sure if that will be a traditional research role or not. We'll see.
Best of luck to you. That sounds exciting.
Yeah, thanks. I mean, it is a bit of a tricky time for science right now. So it's not the worst time to be in school doing a PhD and not be in the job market. Hopefully that changes. But yeah, so far it's still trying to do science.
Great. Thank you so much for joining us today. It's been totally lovely.
Yeah, thank you. Thanks, Lydia. If there's any other questions, I'm always happy to answer them via email, and you're welcome to share my email address with the attendees. Lydia, I appreciate everyone taking the time to hear about my work and for all your interesting questions and engagement.
And we're always looking for new, interesting presenters. If anyone has suggestions, people they know or stuff they'd like to say themselves, we're always looking for fresh blood.
Okay. Thank you so much, everyone. Thank you, Mariam. And we'll see you next month.
Yeah, thank you. Thanks so much. Have a lovely day, everyone. Bye.